All right, so welcome to week 5. You guys have survived midterm week, and you are now in the second half of the course, and hopefully it is all downhill from here. So week 5, we are talking about polynomials. So we're going to be looking at chapter 3, which is polynomial functions. So this is covering quadratic functions and models, which you've seen quadratic equations before. So some of that is going to be review. And then we're looking at polynomial functions of higher degree like cubics, quartics, quintics, polynomial and synthetic division, zeros of polynomial functions, and then mathematical modeling and variation. So there's going to be 5 sections that you're going to be looking at this week. So you may be wondering, why are polynomials helpful? Where might these pop up in class? So they do pop up in business applications, and there are some examples in the textbook that are business applications of polynomials. Usually that's when you're trying to model data and the data is not a straight line. If it has some curves, you may want to try a polynomial. Engineering. So there's a lot of engineering applications of polynomials. One example are roller coasters. Anything that has curves, those could all be modeled with polynomial functions. Roads are one of them, so a lot of civil engineers may be using polynomial functions. Predicting traffic patterns, you can be using polynomials for. In economics and medicine, there's a lot of modeling that goes on. In economics, you're usually trying to model patterns, and things are not always linear, so polynomials give you a lot more variability for things that move around. I just said economics. Medicine, you can model with polynomials with bacteria. We're also going to be looking at modeling bacteria in week 7 when we talk about exponential functions. And physics, there's a lot of things in physics that use quadratics. Projectiles are one of them, and that's actually going to be what you're going to be doing this week in your discussion. Your discussion is going to take the projectile motion equation. We're not doing physics because we're making a lot of assumptions in order to use just algebra on it. If you wanted to add in like air friction or a draft, wind speed, and all that stuff into projectiles, then you have to do physics. We're not doing that. We're doing math. We're just using a basic physics equation where we make a lot of assumptions in order for it to work out nicely. So there are several things that polynomials are used for. You may or may not see these depending on what your degree is, but these show up in the real world. Even if you're not solving polynomials, it's the backbone to something that is in your life. So this week you're going to be using your linear equation solving skills. You're going to be solving a lot of quadratic equations. You're going to be doing tons of factoring. And you're going to be doing graphing. So same old, same things that you've been doing pretty much every single week. So hopefully you're not tired of factoring yet. You are doing it all the time. So you've got your week 5 discussion, your week 5 ungraded practice assignment, your week 5 assignment, and your week 5 quiz. So let's start with the discussion because I did mention that it has some physics behind it. So this is another math-based discussion where you're going to have to do some math. So part 1 is research. So when you hit a baseball, it forms a curve, it goes up in the air, comes back down. That's called a parabola. And a parabola is a quadratic equation, and a quadratic equation is a polynomial. So we're going to be using this week's material that makes a polynomial. So there is a projectile motion equation. You actually saw this equation in week 3. I think it was week 3. There was actually a question about throwing something in the air, coming back on the ground. And so I forget, they called it the position equation. It's also called the projectile motion equation. But that's the equation we're using. So we've actually had a question on an assignment about it already. We're just looking at it in a different context. So we're going to be modeling a baseball, basically. Like when you hit the baseball from a bat, we're going to be modeling how high it goes when it hits the ground. So in order to do this, we're going to be using real data. So that's where the research comes in. So you need to determine the height at which you would hit a baseball, and we're calling that h naught, our initial height. So we're doing this in feet. So if you're hitting a baseball, you have to figure out how high off the ground are you hitting the baseball. So that is a guess. There's no right answer here. Whatever you want to do to make that guess, what I do is just subtract a foot off of my height. Some people say it's around 3 feet, depending on how far you crouch down. I saw somebody take a look at the strike zone and figure out where the strike zone was, and then that's how they determined what the height would be to hit a baseball. So it depends on how much baseball knowledge you have, but you're just estimating the height part. And then you need to figure out how fast the baseball is when it gets hit off the bat. And so that we actually have data behind that because the MLB actually keeps track of that. So that's the average exit velocity. So I am going to, if it will allow me to click on the list, maybe. Oops. Oh, it does not want me to actually click on the list. Well, I've been able to click on the list in the past. It apparently doesn't like me. But if you click on that list, it will give you a list of baseball players, and then it gives like their a whole bunch of data. And so you want the average exit velocity. That is the average speed the baseball is going after they hit it with the baseball bat. So it should be around 95 miles per hour or so, because typically a pitch is thrown at about, that speed, and when you hit it with a baseball, you're trying not to have a lot of friction. So it should come back at about the same speed, give or take, some losses. So you're going to pick data off of that list, and that is going to give you your speed. So that's your research part. Then part 2 is where you actually start doing the math. So your first step is you need to convert that exit velocity to feet per second, because they're giving you miles per hour. But our position equation has to be in feet. So you need to convert your miles per hour to feet per second. And you can just use Google to do that. If you just type into Google, if I spell that right, convert blank miles per hour, and you put in the number 2 feet per second, it will do that for you. So it's really bad handwriting there. I'm trying to squeeze in there. So you don't have to show the work for that. Use Google to do the work for you, and so you should have your speed in feet per second. Usually they're around 140 feet per second, 140, 135 in that arc. So once you have your speed in feet per second, and then you've got your height in feet, then you're putting them into the position equation. So the position equation in the textbook, when we first were introduced to it, was S. We're using H because this is going to be height. In physics, they use S to represent displacement. I don't know why S represents something that starts with a D. I'm not a physicist. I don't name their variables. In math, we use H because that makes sense. So this is a function. You're plugging in your velocity and your height, and now you have a quadratic equation. So then that's where you start using the information from the textbook. So you need to find the maximum height, which is the vertex, and that is covered in section 3.1. And so that is how high this baseball will go. Now I said we're making a lot of assumptions. The assumption we're making with this equation is that the ball is going straight up. So it's basically a fly ball. It's not. There's a different equation for it actually goes into the outfield that requires using trigonometry. We don't know trigonometry, so we're making a lot of assumptions here. So we are assuming the angle is 90 degrees, it's going straight up. And then you're also going to find when the ball hits the ground, which are the zeros. So that's actually using the quadratic formula, so that's 1.4. So you need to use the vertex formula given in 3.1, and then you're using the quadratic formula 1.4, and that will give you the 2 pieces of information here. So after you've done that, then there's the reflection part, and this is great for the discussion and for replying to classmates, is its reflection part. Is what role do you think the angle of the ball would play in affecting the outcome? So I said we're ignoring the angle, we're assuming it's going straight up. So if we didn't assume that and we had to take the angle into account, do you think that the time it hits the ground will change? It'll hit the ground faster, slower? How will the height change? You know, that's where the discussion part really happens. So a lot of people enjoy this. A lot of people into sports really enjoy this discussion because it's like, oh, I had no idea that there was actually mathematical formulas behind sports. There are some additional videos here to kind of talk about this. So there's a projectile, motion, and parabolas, the science of NFL football. So that talks about how you can use a polynomial to model a football as, you know, when it gets thrown or even when it gets kicked and you're trying to make a field goal. The sport of solving quadratic equations, so that goes into where quadratics show up in sports. And then maximum height of a quadratic, or maximum height of a ball quadratic word problem. So basically half of what we're doing. There's a YouTube video kind of going through an example of how to do that. So those should really help you out with the discussion. So moving on to your assignment. So your ungraded practice assignment this week comes from Chapter 3, the end of chapter review exercises. So if you don't have time to do all of those, the checkpoint exercises are great practice as well. And then your graded assignment, you should be, you know, familiar with the routine by now. You've got your 10 questions. This particular week, you have to do the problems in order because you're using the material and like the answer in part A, B, and C is needed to do D. So you have to do this one in order because you're using the prior information to work through the assignment. I have in the week 5 folder where I have all my videos, I have one on polynomials. It's one labeled 3.4. So it should be in the week 5 folder. I actually walk through an example very similar to the assignment in that video. So if you're struggling on the assignment, I recommend watching the 3.4 video where I kind of walk through everything. And that should help you out because I do similar problems, obviously not the same problem, but similar so that you have an idea of what you need to do. Then for your quiz this week, so your quiz is covering week 4 material, so I just want to reiterate that, covers week 4, so that way you can use your feedback from the week 4 assignment to study. So we're back to the 10 questions, 1 hour. Make sure you're submitting your work to the Dropbox. So again, week 4. So it's going to be covering function notation, function combinations and compositions, analyzing the domain and finding the zeros of functions, graphing functions, figuring out function transformations, writing mathematical models, and then finding inverse functions. So it's covering Chapter 2, the stuff in week 4. So I recommend that you review the week 4 assignment because that's going to help you practice for the quiz. The Chapter 2 pre and post tests that are on the textbook websites are good practice. And the worst scoring questions were those on transformations and word problems, the modeling. So that's where these practice problems are coming from. So these are, I've got some on function transformations and then interpreting functionings, interpreting like word problem modeling kind of stuff. So those should give you some practice problems to help you study. So the suggested schedule. So your discussion you can start pretty early because you only need 1.4 and 3.1 essentially. So you can get that done within the first couple of days if you follow the schedule, and then you can focus on the material. So since there's 5 sections, I've got a section a day marked which videos go with which. And as I said, the assignment you have to do in order. So one thing is the first problem of the assignment actually comes from section P.3. So you want to go back to P.3 if you can't answer that one. And then B, C, and D come from 3.2. And then the rest of problem 1 you can do after you go through 3.4. So that's why I recommend watching my 3.4 video. And then question 2 comes from 3.5. So there are 2 questions, but problem 1 has many different parts because you're analyzing a single polynomial and doing many steps with that. So are there any questions on what you guys have to do for week 5? All right, so if you guys have questions, you can send me an email. You can give me a call, of course, and I will make sure to send this out tomorrow as usual. And of course, I'll be sending this out to remind if you've signed up for that. And if you have any questions, of course, you can email me or your instructor. So hopefully you guys have had a great week so far. You had a great week 4, and you're looking forward to week 5 and pushing through. So, all right. So hopefully I'll see you guys next week. Have a great day.